Hello everyone, and welcome to today's joint webinar, TAITherm Underhood Thermal Protection Coupling with an Advanced Open Source Simulation Engine, HELYX. In this webinar, we will depict how a simulation using TAITherm and HELYX can accurately predict underhood component temperatures. My name is Chris Niva, Marketing Operations Coordinator here at ThermoAnalytics. Today's presenters are Sasha Jelic from ThermoAnalytics and Salvatore Renda from ENGYS. Sasha is a key account manager at ThermoAnalytics in Munich, Germany. He has around 15 years experience doing aerodynamic and thermodynamic CFD simulations, mainly for the automotive and aerospace industry, and has been working on topics like engine thermal protection, brake cooling, human comfort, and battery cooling. He has obtained his MSc in aerospace from the Technical University of Delft with a CFD specialization. As a technical expert, he is currently supporting major OEMs in Europe and Asia. Salvatore Renda holds a PhD from Università degli Studi della Calabria with a specialty in computational fluid dynamics. His previous positions focused on higher order discontinuous Galerkin methods within the aerospace industry at DLR in Germany. Salvatore has a history of engineering consulting to complement his R&D experience in various organizations. He is currently a developer and senior CFD engineer at ENGYS, enabling customers across various industry sectors to use ENGYS software tools more effectively to quickly bring value to organizations. Throughout this presentation, you may submit questions in the question box and we will review them at the end. We are also recording this webinar and we'll be sending you the link following this presentation. With that, Sasha, you may begin.
Thank you, Chris. We will present the coupling with the CFD software HELYX elements for an underhood thermal protection case using the DrivAer SUV geometry. We will start with an introduction, introducing the company ENGYS. I will say a few words about ThermoAnalytics. We will explain the coupling methodology and the different applications that it can be used for. We will show the coupling workflow, CoTherm. Then we'll show the results of our case study for the DrivAer vehicle, so methodology, setup, results, and then we'll come to the conclusions. I will now give the word to Salvatore.
Thanks, Sasha. Just a few words about ENGYS. We are a global provider of CFD products and services. We have been founded in the United Kingdom and we are just about to celebrate 10 years of being in business. We have been always focused on enabling the use of open source software in the industry. Members of our company have been OpenFOAM developers since 1999. If you are familiar with OpenFOAM, this came out around 2004-2006, and before it was named FOAM. We have developers in our company which worked on the original FOAM libraries. We have 7 offices worldwide with headquarters in London and other offices in Germany, Italy, USA, Australia, South Africa, and Brazil. We also have an experienced and established network of software distributors in Asia, so in Japan, South Korea, but also in the US, France, and Spain. Few information about our main products. Here there are 4 main groups. The first one is HELYX. HELYX is a general-purpose open-source CFD tool for enterprise. It constitutes primarily of the graphical user interface and the core, the simulation engine. Next one, we have Elements. Elements is an advanced open-source CFD tool for automotive design. This is more like a superset of HELYX. It has all the features of HELYX, plus some additional ones which are more specific for automotive design, external aerodynamics, and this kind of applications. This really improves the productivity for automotive. Next group is the group of the add-ons. First of all, we have an adjoint optimization module, which is based on continuous adjoint optimization. We have also a block coupled solver, which is ideal for turbo machinery analysis, Formula 1, and all those areas which requires a quick turnaround in terms of results. Next add-ons is HELYX Marine, which is used for ship hull analysis and to run seakeeping and calm water analysis. And finally, we have an advanced multi-phase flow package. The last group is HELYX OS, which is an open source GUI for standard OpenFOAM. This is an academic tool. More information on those products can be found on the ENGYS website. So how do we use OpenFOAM at ENGYS? OpenFOAM consists of two main parts, the source and the applications. The source is a set of libraries which includes the fundamentals of the numerics, such as discretization and boundary conditions. The applications are high-level code, which include measures, solvers, pre- and post-processing utilities. At ENGYS, firstly, we have been working to improve the basic libraries, the fundamentals, modifying and expanding the simulation kernel as needed. Secondly, we have replaced some of the existing solvers and utilities with our own ones, with the main focus of improving physics and robustness. Doing this, we have still kept the format compatible with the original OpenFOAM format and same I/O. Over the years, we have introduced and modified more than 3,000 files. Here we can find some innovations at ENGYS that can bring value to our customers. First of all, we have a continuous adjoint optimization module that enables flow control, reduce energy consumption by components, and improve the performance of the design. Next one is the next dominant meshing tool, which is robust, scalable, suitable for complex geometry and physics. Performance and quality of our meshers are superior as compared to the standard SnapX mesh in OpenFOAM. Our meshing tools are included in our HELYX core. Third one, we have feature-rich graphical user interface, which reduce the complexity in setting up cases, increase the productivity, and in general streamlines the analysis process.
I will say a few words about ThermoAnalytics. So TAITherm is our main software for doing the 3D simulations. And we can use CoTherm to couple to most CFD codes, like Star, Fluent, and OpenFOAM. We can also couple to 1D system tools, like GT Suite, Amazon, and MATLAB. Today, we'll focus on coupling with HELYX elements. And with this, we can look at different applications, like the battery extension. We can simulate the exhaust using the exhaust gas flow. We can do multi-variable drive cycles and look at the human comfort simulations based on the Berkeley comfort model. Here's a typical example where we're simulating the full 3D geometry of a vehicle. We're simulating this transiently. You see that we're simulating here 10 to 20 minutes, and the temperatures are fluctuating over time. We can simulate this easily without a lot of computational resources. When it comes to the coupling methodology, so you see here the basic process where TAITherm is calculating the radiation conduction and then mapping the surface temperatures on an element base to the HELYX core, which is then calculating the convection, so calculating the heat transfer coefficients, fluid temperatures, and mapping that again to TAITherm using a neutral file format. So the applications that can be used are, for example, engine thermal protection, followed by idle soak, brake cooling, human comfort, battery modeling, and many more. The different ways of coupling, we can couple steady state to steady state, steady state to transient, and transient to transient. The coupling process in CoTherm is shown here. So what I just explained before, that is represented here, the block diagram. We have the run thermal, the run CFD, and the temperatures of the different components can be modeled and monitored over time, see how they evaluate or if they are stabilized. So this is a ready-to-use template. The only thing that needs to be done is setting the installation path and maybe some other options like the amount of processors that you want to run on. And then this is a fully automated two-way coupling process. And looking at the results for the case study of the DrivAer vehicle. So first, vehicle constant driving speed of 140 kilometers per hour. Then the vehicle comes to a stop and we simulate 20 minutes of key-off soak. Ambient temperature of 30 degrees C, and we use the exhaust module for our exhaust gas modeling. So in TAITherm, the boundary conditions, first you need to define the material properties and the emission coefficients, and then model the heat sources. So the exhaust system, the hottest part, we model that with our exhaust module, and the exhaust gas here is represented with a fluid node network, fluid stream, where you define your exhaust gas mass flow and entry temperature, which can vary over time. And with this, we calculate nicely the exhaust gas temperatures through the exhaust. We include the effects like the pulsation of the engine, which increases the heat transfer, surface roughness, boundary layer buildup, and when there are bends or expansions, we adjust the HTCs locally. Furthermore, we have a model for the turbo, catalyst, and the mufflers.
Now some words about the CFD setup, meshing and setup. We have measured this car with our own mesher, and the max cell size was 0.96 meters at the free stream. Minimum cell size was 1.9 millimeters. We placed 3 layers on all over the wall surfaces with the coverage above 99%. The total mesh size for this case was 21 million cells, and we used multiple surface and volume refinements to capture all the relevant flow features. There are 2 cell zones into this model to identify the rotating region, the fan, and the porous region, the radiator. I want to mention that this is a coarse mesh that we just created for the sake of the demo. We generally run aerothermal problems on meshes between 150 and 300 million cells. In terms of setup, we used our own solver with enhanced buoyancy numerics for better performance in terms of accuracy, robustness, and convergence. We ran this as a steady state run solution. We could have used something more complex like DS, but as I said, this was for the sake of the demo. For the turbulence models, we use K-omega SST, and buoyancy, the Bustinesque approximation. In the constant speed phase, we switched on fan and radiator. The fan was modeled with multiple reference frame model, and the radiator was modeled with the Darcy porosity model for the flow resistance, and the fixed temperature its source of 80 degrees C for the thermal side. We also have more advanced heat exchanger models for the radiator, like the effectiveness heat exchanger model, which takes into account the coolant properties and flow rate. During the soak phase, fan and thermal side of the radiator are switched off, so we just consider the flow resistance. In terms of boundary conditions, for the constant speed phase, we modeled the wheels with rotating wall velocity, and we used the classic wind tunnel configuration, so like inlet, outlet, and slip walls for the sides and tops. On the soak phase, wheels and ground are switched to fixed wall, and the sides are changed to openings. This is basically to model an atmospheric plenum. On the wall, for the temperature, for the thermal boundary conditions, we use map from file, which is a boundary condition developed to read the NTL file written by TAITherm and to map the temperature into the CFD. A few pictures of results for the steady state phase taken from the CFD. On the top row, we have some temperatures. On the left, we have the surface temperature on the hood. The range is clipped at 130 degrees C. So in red, we can see all the areas above this critical temperature. On the right side, we have an isovolume with a threshold above 70 degrees C. So it's basically the fluid volume above this temperature. This can be used to isolate critical areas. On the bottom row, we have velocity streamlines and some picture of the flow field, of the velocity field on the symmetry plane.
On the TAITherm side, you can look at the surface temperatures. TAITherm is mainly a shell-based solver, which means that you don't need to solid mesh all the components. You can just specify a thickness. So when looking at this heat shield, it's modeled as a shell, and you can actually even define multiple layers. So for example, saying this is 1 millimeter aluminum, then an isolation layer in the middle, one layer of aluminum again. You could solid mesh all those layers, but that's really not needed here. However, for certain components, you could solid mesh them. All right, so then you see clearly the temperature drop here over the heat shield. And furthermore, you can look at where the radiation is coming from, which is not always the nearest part. Looking at the breakdown of the heat fluxes, so you see that this point on the heat shield is mainly receiving radiation, but it gets a lot of convective cooling and a bit of conduction to the neighboring elements. Then, looking at the soak results, so after the steady state vehicle driving, the vehicle comes to a stop, and then the exhaust and the engine are still very hot, but there's no cooling airflow anymore. That means that all the parts in the vicinity of the exhaust will immediately start to heat up. And also, you have a hot air temperature rising due to buoyancy effects. You see that in the lower images. So on the left, the steady state phase, where the hot air is coming out of the heat exchanger. But then when the vehicle stops, in the first minutes, you see high temperatures rising above the engine, which then slowly cool down. So when we simulate this in a coupled approach, where we couple at certain instances, you see nicely the temperatures rising of the different components, where some parts will peak after already 1 minute, and other parts will have a peak later at, for example, 4 minutes. So this depends on the one hand on the heat transfer, that's radiation, conduction, convection, but also the thermal mass of the different parts. And what you then see in the animation is that above the engine, you see the temperatures rising and then slowly decreasing again. Coming to the conclusions. So we've shown an integrated coupling process between TAITherm and the HELYX core. TAITherm takes care of the radiation and the conduction. HELYX simulates the convection. This is a two-way automated coupling process. We have ready-to-use templates for steady state and transient scenarios. And this can be used for applications like engine thermal protection, exhaust, battery, human comfort, electronics, etc. And for all this, we can provide best practices. For more information, please check our websites or send us an email.
Okay, thank you, Sasha. We do have some questions. Are there concerns with the mapping process if you mesh the thickness of a thin part in CFD for the sake of the flow, but only use shell elements in TAITherm?
If I can answer that, no problem at all. The mapping takes place based on normal vectors, so it knows very well which side it needs to map. And yeah, you can use shells in TAITherm, a volume in the CFD, or shell in CFD and shell in TAITherm. Both will work.
Okay. How does HELYX handle official OpenFOAM updates?
So in terms of updates, we tend to port the features which our customer likes. So we generally try to keep on track. We have a base version and we try to backport and keep on track with the things which looks more interesting for our customers. And of course, we find things which are not implemented in the optimal way. So sometimes we just re-implement them from scratch as features in HELYX core.
All right. Have you used lag elliptic blending or elliptic blending turbulence models instead of K-omega SST? Any benefits?
Yes, we have this turbulence model, and we haven't tried on these specific applications, but we have this turbulence model, and this is production ready. We have customers running this.
Okay, and that will do it for questions. Oh, here we go. One more actually just came in. Is this finely coupled workflow well established in the automotive industry?
We are using the CoTherm coupling process for many applications and at many different customers for any kind of CFD tools. So it doesn't matter which application, which CFD tool. This is certainly an established process.
Okay, we've had a couple more come in. It looks like there was a very distinct outflow of hot air through the grill and soak. Have you given this detail some attention?
The hot air will start to rise, obviously, because there's no vehicle speed anymore. So there's pure natural convection, and you have very hot components like the exhaust and the engine. So the air will start to rise, and obviously it needs to go somewhere, right? Quite some will remain above the engine, but anywhere where there is an outlet, so the wheelhouses or the grills, it will go up. And this is what we typically see.
Okay, thank you. Many CFD solvers have implemented radiation solvers. What is the advantage of coupling with TAITherm versus using a CFD solver alone?
All right, typical question. So some of the features I have shown, like using the shell-based solver. We have the fluid node network, like I've shown with the exhaust module. Thermal links I like to mention, where you don't need to mesh connect different components, but I think the most important one is that we're able, as you've seen before, to do highly transient simulations using a coupled approach between TAITherm and CFD. You've seen the engine, 10-20 minutes of very fluctuating engine or exhaust gas temperatures. We can easily simulate this on just a few hours on a machine, and that is very difficult when using CFD standalone.
Okay, to follow up on that, how long does it take for the whole simulation and on how many processors?
All right. This simulation is coupled, right? So TAITherm itself runs really fast in just a few hours. When we couple for this soak, case, which is a quite complex scenario. As mentioned, we couple at different points in time, do transient time steps. So this process takes a couple of days. I can give a bit more detail. So we used here a demo case with a bit coarsened a volume mesh just for the demo purpose. But on the other hand, we ran on only 64 processors. We can do this in a couple of days. But on the other hand, it's no problem to run on 400 or 500 cores with a more detailed mesh. So yeah, that should give a kind of idea of the runtime.
We run roughly 10 CFD solutions, so we coupled 10 times, and every CFD solution has subloops in the coupling with TAITherm.
Okay, how does HELYX calculate the HTC and T fluid? What distance from the wall?
There is an application, we have some applications and function objects to do this, and there are two options. You can specify a bulk temperature as input parameter and use this to evaluate the heat transfer coefficient, or otherwise you can take the software, you can leave the software taking care of measuring, of getting the near wall temperature at the first cell.
Okay, what is the frequency for the switch between TAITherm and HELYX?
So in this case, we run, I think, 6 subloops, and settings were not optimized. The CFD was run for 1000 iterations, and after that, we start to run TAITherm and updated every 500 iterations. So the updated frequency would be every 500 equal iterations. Those settings can be still optimized.
Okay, is the ENGYS mesher able to use the TAITherm FEA style mesh as input geometry?
So the ENGYS mesher can read the triangulated surfaces. So as long as you can export into STL or OBJ, you can get these. Or we also have support like for Nastran and Nastran meshes. And in particular, here in this case, we used to have the mesh in 20L file, the neutral format of pattern.
Okay, and then is the time stepping the same between OpenFOAM and TAITherm?
So for this case, we run HELYX as steady state, whereas we run TAITherm as transient. And the points that we run, they are like at in time, there is a different density spacing. So at the very beginning, when there is the peak, we captured more, we used more points, and we captured to capture the peak. And after that, like we run like larger steps.
All right, and then one more. Can we use TAITherm early in the design phase as well?
Yes, certainly. We can model the design digitally, run different variants, try out different materials, different heat shields maybe. So all this can be done virtually without a prototype.
Okay, looks like that's it for questions. That will complete today's webinar. We appreciate you all attending, and thank you, Sasha and Salvatore, for presenting. If you do have any further questions, please do not hesitate to reach out to us, and we'll hope you join us for future webinars. Have a great day.